Okay, we continue with the SPICE netlist, which is the heart of any SPICE file, which contain a list of components and the nets or nodes that connect them together. It describes the position of each element in the circuit according to the nodes in the circuit and the element's parameter. In the Tenor tools, the netlist is in the form of file name, whatever name that you give, .sp, that is from the schematic, and for the layout it will be a file name .spc. For the synopsis, it is just called netlist. Once you have run the simulation, another file will be created, which is hspice.list, which is generated from the input.spi file. In the LVS, the netlist file will be compared between the schematic and the layout to check whether the design are equal and match. The format and syntax might be different from one company to another, but basically an asterisk at the beginning of a line indicated it is a comment. Comment is very useful to label circuit section, including some nodes and everything. So this is example, asterisk over here. So meaning that this is all comments, okay, separating the model, the netlist, the stimulus. Okay, so this is an example of rc.sp describing the behavior of the circuit, which consists only three elements: Vin, R1, C1, Vin, R1, C1, Vin between input and ground, in and ground. It is PWL. This is the PWL of this particular Vin. R1 2K, R1 between input and out nodes, the value is 2K, and for the capacitor between out and ground, and the value is 100 femto. In, ground, sorry, out and ground, and the value is 100 femto. So in this, you will do a trend analysis from 20 picosecond to 1 nanosecond, and we plot V in and the V out. And any SPICE file will have .n to indicate the end of the netlist. In the printing and plotting result, you can have a .print or .plot. .print just, it will print the value of whatever you want. The AC analysis, the transient analysis of these voltages, or plotting the graph in transient and AC analysis. So this is one example, graphical result of V in and V out. So this is .plot actually. Okay, so the input, the black one, the output is the blue one. Okay, and for the sources, because all the circuit must have a source, the most important is the DC source, which is a constant. You can have a voltage or current. This is how is the syntax, the name between the nodes N1 and N2, the type, and the value. Okay, you can read over here, N1 and N2 type, value. For example, V in between node 2 and 0, it is a DC, the type, and the value is 10 volt. VDD between VDD and ground node, the value is 2.5. IS, which is a current between node 3 and 4, it is a DC current with a value of 1.5 amp. And for sinusoidal waveform, similarly, you have a name between which nodes, okay, and this is the type, which is sine, and this is describing the sine wave. VO is the offset, amplitude, air frequency, delay, theta, and phase. Okay, if TD, theta, and phase is not specified, it is assumed to be 0. Okay, this is an example of a sine wave of 50 Hertz over here with amplitude of 10. There is no delay. Okay, for the cosine wave, similarly, it is sine also, but you have to indicate a 90-degree phase difference between sine wave and cosine. For pulse source, which is usually used for clock or regular input AB to the digital circuit, this is how to describe that. The name between which node, it is a pulse type, the value, and V1, V2, initial and the final value, delay time, rise time, fall time, pulse width, which is the on time, and the period. Okay, delay, time rise, pulse width, time fall, and the period for one cycle. Okay, this is how you describe one type of pulse signal. This is a piecewise linear source, which is arbitrary signal which doesn't have a specific, and it is irregular in shape. So at 0, this is the value V1. At T1, the value is V1. At T2, the value is V2. At T3, the time is V3, and so on. Okay, so you have a regular shape. And the analysis in SPICE, usually we'll do the DC analysis to check what is the output if Vin is constant, and then a transient analysis, what is the output if Vin changes, and other from this you can do the AC analysis, that is regarding the frequency. This is example of DC analysis of the circuit. We have VGS, VDS, just a transistor. So this is VGS, VDS, M1, your transistor. Between gate and ground for VGS, drain and ground for VDS, and for the M1 is between drain, gate, and source. This is your buck, the fourth terminal, and it is NMOS. This is what we want, a DC analysis. We sweep the value of VDS from 0 to 1 in 0.05 step. VGS also we increment from 0 to 1 at 0.2 step. And this is what you get, the output. Okay, we vary the VDS, we vary VGS. So we have the IV characteristic of NMOS transistor. This is an example of transient analysis of an inverter. We have one input, the source, PMOS and NMOS. So you have also VDD. Okay, I forgot to mention this is VDD. Okay, so you have VDD, Vin, two transistors just now, M1, M2, which is NMOS and PMOS. Okay, and then we do a transient analysis from 0.1 picosecond up to 80 picosecond. This is what we get. Okay, when the input, which is VA, the black one, is 0, your output is high, which is the output of an inverter. It is correct. At 1.8, the value of 1, logic 1. And when the input is 1, the output is 0. But at the transition, we have overshoot over here. This is what we want to see. What will happen if the rise time, fall time is different. And similarly, when the output goes to 0, the output goes to 1, and we have overshoot also over here. This is in picosecond. And also we can have a sub-circuit in the netlist. Dot sub-circuit, the sub-circuit name within which node, the sub-circuit definition, and all the sub-circuit ends with .ends. It is like a subroutine in any software programming. Okay, and then this sub-circuit will be used in the main circuit to do the simulation. So this is an example of sub-circuit of inverter between node A and Y, describing just one transistor over here, inverter. So we have two transistors, M1, M2, NMOS and PMOS, with all the model over here. And then this sub-circuit will be used, for example, if you want to cascade several inverters like this, this will be used in the main netlist. Okay, actually you don't have to write this. You just draw the circuit in the schematic editor, and this will be translated into the netlist. Okay, another example of netlist, sub-circuit carry A, B, C, the input, C out. So this is actually the sub-circuit of a carry out for a full adder. Okay, now I'm trying to show you the netlist for NOR gate that I have run using Synopsys. First, I draw the circuit for the NOR, 2 parallel and 2 transistor in series. So the input is VA, VB. I name all the nodes, VDD supply. The output is over here. This is the bottom cell. Okay, so I save this as a symbol. Okay, and then I use that in the test bench. So just now I have saved that the NOR gate, and then I use in the top cell, I just draw the input VA, VB to the input VA, VB. Of course, VDD, we need a power supply over here. The output VO, VSS is the ground. So this is another cell, the top cell, the test bench. So what is created in the netlist? Okay, so this is the sub-circuit describing the node just now. Okay, you have 4 transistors. Okay, and then we have another one right here that we use the NOR circuit in the test bench, and with the 3 input V1, V2 and V3. Okay, so in the bottom cell just now we have 4 transistors over here, M1, M0, M3, M2. M1 is between VO, VA, so this is your M1. Okay, between VO, VA, the input coming from here. Okay, VSS, VSS, the source is VSS, the fourth terminal bulb is also VSS. Similarly for MO, input the VB, and M3 over here, VDD. Okay, and then we have M2. This PU is actually, I named this line as PU. Okay, so this will describe the circuit. This is the netlist sub-circuit. And then at the main, the test bench, we have 3 inputs. I have 2 DC pulses right here, V1 and V2, and I have a DC source over here, which is to power up the NOR circuit. So I run a transient analysis between 0 up until 50 nano at time step of 3 picosecond. So this is what I get, the input just now. Okay, I run using the 90 nano library. Okay, and this is the output. Okay, you have VA, VB, and this is V output. Since it is a NOR 0, 0, you have an output of 1. My DC just now is 1.5, so the output is 1.5, which is logic 1. The rest, either input is 1, the output will be 0. There is some glitches over here. Okay, so if you look over here, V2, which is my VB, the top one. Okay, it is a DC 0, meaning that it start from 0. Okay, I have a delay, the value is 0.5, the maximum 0.5, a delay of 10 nanosecond, and it start with rise time, fall time 1 pico, pulse width is 10 nano. Okay, and a period of 20 nano over here. Okay, similarly for A, okay, 0, okay, 20 nano, this over here is 10 to nano, the period is 0 to 40 nano. Okay, and my rise time, fall time is pico, but the period is in nano. But if my rise time and fall time is different, if I increase the rise time, fall time, I have a slope over here. And this one, I didn't use a delay, so it start from 0. Okay, pulse width, this is the period. Okay, 0, 0, output is 1, so it is the correct answer for the NOR circuit just now. Okay, I'll talk about the hspice.list later.